Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Okay. Today I will explain about the bipolar junction transistor for the basic bipolar junction transistor. Okay, maybe I just give the important thing about the bipolar junction transistor, and I suppose you have learned about bipolar junction transistor from my PPT that I attached in last week. Okay, so the first transistor is designed at Bell Laboratory, who design is Dr. William Shockley, and then Dr. John Bartlett, Dr. Walter Hybretten. Okay, so of three of these guys shared a Nobel Prize in 1956 for this contribution. So the bipolar transistor is very important device in electronics and also in other electrical engineering field, because of not only in low power application, the bipolar junction transistor also can be used for high power applications. Okay, so basically the bipolar junction transistor is consists of three terminal, emitter or E, and then base or B. This is the emitter and this is the base and this is the collector. Okay, so basically the bipolar junction transistor is we designed by the diode, and then we connect two diode. We got the bipolar junction transistor. There are two types of the bipolar junction transistor. The first one is PNP. PNP is mean that the P type for emitter and collector, and N type for base. And then another is NPN. NPN is mean that the N type for emitter and collector, and P type for the base. And we have two supply here. We have VEE and VCC here. VEE connect to emitter to base, and then the VCC connect from the base to collector. Okay, and then the emitter layer is heavily doped, and then base is lightly doped, and collector is only lightly doped. Okay, so why we dope in different parameters to trio terminal? Because of we want to create something that is a new or that is a different with the diode. Okay. Okay, so we can see from here that the emitter is highly doped, so the energy level like here, and then the base is lightly doped. This is the NPN transistor, so it's lightly doped, and then the collector is also lightly doped. So the energy between the emitter, base, and collector we can draw like this one. So the working principle of the bipolar junction transistor is we can transmit, or we can deliver current from the collector to emitter by controlling the base. So in BJT we control the current. So current control current source. So this is the BGT, and for FET is voltage control current source. So basically we want to deliver a current from the collector to emitter, or we deliver an electron for emitter to collector in NPN, and then we can deliver a current and by controlling the current using the base terminal. So it means that if we want to deliver a high current from the emitter, from the collector to emitter, we have to open the gate. We have to open the base more. If we want to deliver a small current from the collector to emitter, we decrease the gate in the base. So this is the basic working principle of the bipolar junction transistor. Okay, so this is the PNP. So if we control by using the control in the base here, we can deliver the majority carrier from the emitter to the collector. So from the PNP, the majority carrier is whole. So we can control the whole from the emitter to collector, or okay. And then if we how to deliver a current, how to control the current. So the first one is, if we want to deliver a current, we have to put the BJT in the saturation region or the active region. We have a three kind of the mode of three mode in the BJT. The first one is saturation current, and then active region, and then a cut off. Okay, so if we want to deliver a current, we have to put the bipolar junction transistor in saturation mode or active region mode. But if we want to turn off the BJT, we put the bipolar junction transistor in cut off mode. Okay, so this configuration is the forward bias or active region. In active region, we forward the junction between the emitter to base. Because the emitter is p-type, so the forward bias is mean that we connect to emitter to the positive here. So this is the forward bias. And then and another thing is we connect collector to base in reverse bias, like this one. So this reverse bias, it means that this is collector is p-type, so connect to negative terminal here. Okay, so after we connect the terminal using the appropriate voltage. So for example, the first one, we connect the emitter to base in the forward bias. So the depletion region between the emitter and base become smaller. So the majority carrier in the emitter can pass the barrier. So the majority carrier can flow from the emitter to the base terminal. And then in another hand, the collector to base is connect in reverse bias. It means that the depletion region here is large, so the barrier is become very large. So the minority carrier cannot flow because of the barrier, but the minority carrier can flow through the barrier. Or the minority carrier in base is because base is n-type, so the minority carrier is the whole. So whole can transfer from the base to the collector. So the majority carrier plus minority carrier here. So this is the total of the current. So IC is the majority carrier plus I minority carrier. So it means that here this is majority carrier and plus a minority carrier. And then if we apply the Kirchhoff law here, we have the current here, IE here, is equal to IC plus IB. This is the IC, this is the IB. IC is the collector current and IB is base current. Okay, so this is the energy level in the BJT, and we have three configurations to connect the BJT. The first one is common base configuration. Common base is base is connect to the ground, and common emitter, it means that the emitter connect to ground. Common collector is connect to ground. So we can see here the base is connect to ground. This is the ground and this is the base. So this is for PNP and this is for NPN. This is the forward bias or active region, because of the emitter is connect to the positive and the collector connect to negative here. So it's similar to the NPN. So we can draw from this configuration using the characteristic. We plot the VBE based to emitter voltage here, or VEE. okay, here. And then this is the IE. IE is the emitter current. So if you see, this is like a diode because the connection of the emitter to base is the forward bias. So if the we use the silicon, so the Kni voltage is 0.7. So before the 0.7 or in this area, so the current didn't flow. But after the voltage passed the Kni voltage, the current can flow like this one. And then another, we can draw another picture here. This is the VCB. VCB is the collector to base voltage, or here. This is the collector or VCC here. And then this is the IC. IC is collector current. We can see here, if we connect VCB very large from 0 to 20, so the IC or collector current is still remain or stable here. So it's like a saturation here. Depends on the emitter current. So the IC or collector current is not depend on the variation of collector to base voltage or VCB here, but the IC is depend on the how much the emitter current. So we can see here, if IE, this is the IE is 7 milliampere, so the IC is 7 milliampere. IE is 6 milliampere, also 6 milliampere. So it means that the IC is equal to IE, yeah, because of the IB is very small. Here, okay, so yeah, we can see here we have a three mode. The first one is cut off, and this is the active region, and this is the saturation region. I forget to explain about the three mode in BJT. So active region is mean that we connect the like this one, okay, emitter to base in forward bias and collector to base in reverse bias. And saturation region we connect to supply voltage in forward bias and cut off both of the power supply in reverse bias. So this is the difference mode of the bipolar junction transistor. Okay, so this is the characteristic of the transistor. The first I explained before. If we draw the voltage between the base to emitter and then we draw the IE, emitter current, we can see it's like a diode here. So this is the actual characteristic. This is the approach characteristic, and this is the ideal characteristic. Okay, and then in BJT we are familiar with some parameter. The first one is alpha. Alpha is the comparison between the IC and IE here. So alpha DC is equal to IC per IE. And then we can see from my previous explanation that IC is equal to IE. So for ideally the alpha is equal to 1, or practically is from 0.9 to 0.998. And then IC is this one. This is from majority carrier, and this is from the minority carrier. Okay, I explained before. Okay, and then how the transistor is transferring resistor, or this is a transistor. So how the transistor can amplify the current? So we can see here, this is the input voltage of 200 millivolt, and then this input voltage has input resistance of 20 ohm. Okay, we connect the transistor in common base. Common base, it means that the base is connected to ground. This is the connect to ground. And then we have the output resistance, typically from 50 to 1 mega ohm. So they choose the 100 kilo ohm. So we can see here how to explain that the transistor can amplify the current. We notice that the input voltage is 200 millivolts. So IE, or the input current, is VI per RI here, Ri here. So we can get that to 100 millivolt per 20 ohm. So we get 10 milliampere. And then we assume that the alpha AC is equal to 1. Okay, so alpha AC equal to 1. So alpha is equal to IC per IC per IE, like this one. Okay, so it's like this is the IC here, and this is the IE. So it's equal to IL per IE here. So it means that because the alpha is 1, so IL is equal to IE is 10 milliampere. So VL here, the voltage in load is IL dot R. IL is 10 milliampere. Okay, R is 5 kilo ohm. We got that 50 volt. So the amplification voltage is AV, or voltage amplifications. VL per VI is equal to 250. So this is the amplification of the common base transistor. And the second is common emitter. Common emitter is mean that the emitter is connected to ground here, like this one. Okay, so this is the characteristic of the VB. So this is the VB, base to emitter, and emitter ground. So the VBE is equal to VB. This is the VBE. And then it's like a characteristic of diodes, though this is the characteristic of diode is using a silicon. Okay, VBE versus IB, we can get that before the 0.7, the current is very small or no current transfer in BJT, and after the 0.7, after the knife voltage, the current in IB is become very large. And then this is another characteristic, VCE is the collector to emitter voltage here, or VCC, versus the IC. So we can see that if we control the IB here, IB is from 0 microampere to 90 microampere, we got that IC is make a variation from 0 to 7 milliampere. Okay, so here we can see that the first one, if we use the common base before, we have the alpha, and if we use the common emitter, we have the beta. The beta is IC per IB here. Okay, so typically beta is from 50 to 400. Okay, and then this is the beta, and then this is the beta DC, and the beta AC is delta IC per delta IB. And then beta AC is we can call it a common emitter, or forward current, or amplification factor. If you looking for the datasheet, beta AC is referred to HFE, small, all is small, H small, FE is small, and beta DC is HFE, large FE, and beta AC is HFE, all in the small letters. Okay, and then so how to determine the beta AC here? Beta AC is delta IC per delta IB, so we can use like this one. So if we have the data sheet like this one, VCE versus the IC, so we mark 2 points here. The first one is IB1 here and IB2 here. And then from IB1 we got the IC1 here, and from IB2 we got IC2 here. So delta IC is IC2 minus IC1, and delta IB is IB2 minus IB1. So we're gonna get that 100. The beta AC is 100. And if we calculate the beta DC, IC per IB. So for example, in the middle of this comparison, so we can get that this is 108. It's not very far from beta DC. Okay, so this is the correlation between the beta and alpha. So you can see from here, IE is equal to IC plus IB, and we know that IE is IC per alpha, and IB is IC per beta. So we can replace using this equations. So finally we got that alpha is equal to beta per beta plus 1, and beta is alpha per alpha 1 minus alpha. Okay, so and then IC is beta IB, and IE is beta plus 1 IB. Okay, so the last one is common collector configuration. Is similar to emitter, but in this case the collector is connected to ground. Okay, so common collector we use for impedance matching purpose like this one. Okay, so this is the limits of operation of BGT. If we use the BGT, we have to check the maximum power, or like this one, PC max is equal to VCE dot IC. So in white, this is the safe operation of the BGT. So if we use the voltage more than 20 volt of VCE, or IC is more than or in the shaded area like this one. So this is not safe for BGT. So it's upper the limits of the BGT. So we have to put the characteristic of BGT in the safe operation or in white area like this one. Okay, so this is the example of transistor specification sheet. So we can see maybe you can learn how to read in the electronic laboratorium and also the transistor testing. Okay, I think this is enough for the basic BGT. Thank you very much for your attention. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.